Okay, class. So in this video, we're going to be learning about variational theory, which is one of our two most common types of approximation method. So there really are many more types of approximation methods that are used, but variational theory and perturbation theory are the two most commonly used, particularly for quantum mechanics. So what is variational theory? So variational theory really means we're going to guess, and then we're going to keep tweaking our guess until it's as correct as we can get it. So the very first step that we would do in variational theory is choose some guessed trial function phi. Now, there are some conditions. This guess can't be horrible. We need the guess to be somewhat close to reasonable. And so one thing that we should check always and forever is it should have the correct boundary conditions, right? If we don't have the correct boundary conditions, then we're certainly not going to get anywhere near the right answer. And the other thing is that it should have at least one, but it can have many variational parameters. And in fact, the more variational parameters you have to optimize, in theory, the better you could make your answer, but it gets a lot more complicated. So when computers use variational theory, right, so if we're doing computational chemistry where we're using variational theory, it's completely reasonable to have many, many parameters. But doing it by hand, we usually only want one or two variational parameters when we're doing this by hand. Otherwise, the problem's going to get out of control really quickly. So once we have what we think is semi-reasonable guessed trial function, right, this phi, what do we do next? So the next thing we're going to do is determine the expression for the energy of phi. And so the energy phi has kind of a funny form. So we're familiar with the numerator, which is integrate over all space, our trial function phi, complex conjugate, so phi star, and then we're going to take our Hamiltonian and apply it to phi, right? And so that product gets integrated over all relevant space. That's what we're used to seeing. What is this bottom part? So we have a denominator all of a sudden. We're dividing by phi star phi. So what does phi star phi look like? If we replaced phi with psi, what would this be? It would be the probability function, and when we integrate the probability function, that should go to 1, right? And if it doesn't, that simply means that our wave function is not normalized. So the purpose of this denominator is actually to ensure that our wave function is normalized, because oftentimes it's not. So this is going to correct for non-normalized guess wave functions, or phi, right? And so another note to think about here is which Hamiltonian should we use? We have many Hamiltonians. They change whenever we change our system. And so here we want to choose the Hamiltonian from the most similar model system. And remember, our model systems are particle in a box, harmonic oscillator, rigid rotator, and hydrogen atom. So we want to choose the one that seems most similar to the system that we're studying. And so once we figure out this expression for phi, which involves doing two integrals and then dividing them, and presumably, right, the whole reason we have a variational parameter is that we're going to end up with some expression that is a function of our variational parameter, which might be alpha, it might be c, it could be a, it could be anything we want. And so the third step is going to be to minimize, find the minimum or the optimal value of that energy, which we're always going to consider to be the minimum value. And we'll talk about that more in a minute. So we're going to minimize the energy as a function of this variational parameter. Could be alpha, could be called something else. And to do that, calculus tells us we want to take the first derivative, because when the first derivative equals 0, that's where minimums and maximums can occur. And we're going to assume that this is going to be a minimum because we've set this up correctly. So generally, we don't have to worry about maximums here. There are some exceptions to that rule, but for the purpose of this class, I will not give you a problem where you have to concern yourself with determining between a minimum and a maximum. So we're going to assume that the minimum always occurs when the first derivative of the function energy of phi with respect to its variational parameter equals 0. And this could be with respect to many of its variational parameters, but then we have to get into partial derivatives. We'll let WebMO do that. We will not be doing that by hand. Okay, so once we get this minimum energy, what does that mean? What do we have at the end? We have a minimized energy, and we have this, and it might be an expression, it might still be a function. Presumably we have this alpha that we plug back in, and at the end it's really just a matter of constants. So it's a value. This energy, this expression, once it's minimized, is always going to be an upper bound to the real energy. So this is sort of the foundational assumption of variational theory, is that E phi is always greater than or equal to E real. So the fact that we've minimized it as much as we can means we've gotten as close to the real energy of our system as we possibly can. And so the better we can minimize it, the closer it is to the real energy. So this is sort of a foundational premise of variational theory, is that energy that we find is an upper bound to the real energy. All right, so you may have looked at the WebMO lab activity for this week. You may not have. If you haven't yet, you'll see these soon, and this will make a little more sense. But both Hartree-Fock, or HF theory, and density functional theory methods within computational chemistry and within WebMO, they're the first few options you see under the theory menu, are largely based in variational theory. And so you can actually see the minimization of the energy and the output file that you get when you run a geometry optimization by looking at the geometry optimization sequence. And so in the introductory WebMO video, I tell you how to do that, and I show you that. And I would advise strongly that you look at that. It's actually pretty cool, but you can see variational theory in this sense in practice. All right. So the next video is going to work through an example problem in detail.